participating. I'm very proud to be here and at the same time concerned about the immense responsibility of presenting such an important and difficult subject. The first time that I heard about energy relate to mechanical power was in a lecture by Dr. Marini in 2018. And I confess that it was not easy to assimilate that pressures and tidal volume could turn into energy, and how ventilation could be analyzed through energy. This fact that intrigued me and made me interested. And when the COVID pandemic arrived and put modern ventilation to the test, I began to analyze the influence and correlations of mechanical power with the components of mechanical ventilation, as well as between them. In addition, I performed some correlations with outcomes in patients with COVID and burn patients with moderate ARDS, seeking an expected value for these conditions. I will start by recalling a fundamental concept about mechanical ventilation. The intention of mechanical ventilation is to rest the lungs and improve oxygenation. However, it is components such as respiratory rate, tidal volume, flow, and pressures are misused with an increase in mechanical power. The likelihood of ventilation-induced lung injury will increase. Ventilation-induced lung injury was defined as the lesion derived from the application of mechanical ventilation as a result from the setting of mechanical ventilation and the condition of the lung parenchyma. Although some authors believe that heterogeneity possibly influenced VIL, regardless of the quantification of the ventilation components. This slide refers to ventilation-induced lung injury, barotrauma, volutrauma, atelectic trauma, biotrauma, and ergotrauma. In 1990s, the improvement in survival through the reduction of tidal volume and plateau pressure changed the focus of attention to variables associated with stress and strain, with the use of lower pressure and tidal volume. Thus, the main strategies of mechanical ventilation aim to reduce stress and strain, that is, plateau pressure and tidal volume, in order to minimize barotrauma and volutrauma, respectively, as well as to maintain an adequate PEEP and avoid electric trauma resulting biotrauma. However, the ergotrauma generated by the power of mechanical ventilation, among the mechanisms that cause VIL, remain without received the due importance. "25 years after conceptualization of VIL and understanding its biophysical cause, that is, just recently, focus on pressure and volume has been redirected to energy and power load to minimize VIL. Energy supply in excess to respiratory system during mechanical ventilation seems to be associated with edema and injury. But no variable or phenomenon can be imputed alone as responsible for VIL, and that a combination of pulmonary conditions such as heterogeneity and vascular pressure are associated with the ventilation strategies. VIL results from mechanical ventilation configurations and the conditions of lung parenchyma related to its size and heterogeneity. It is necessary to resolve the injury that determines the change in lung mechanics, as well as to allow enough tissue restoration. Otherwise, it is inexorably heading towards the irrecoverable vortex of VIL. Power is a concept that simplifies the assessment of mechanical ventilation by portraying it by unifying two sets of this that is based on this reasoning, the effects of components should not be considered separately, but they are considered by the effect of the set, their set. The who appears to be more important than the individual and seems to be the best way, the unification. The unification comprised of plateau pressure, driving pressure, P, tidal volume, flow, respiratory rate, resistance, and elastance. And this feels like a new way forward. By the way, the unification will allow to obtain the mechanical power, which is the energy transferred to the respiratory system by the ventilator during a certain period in joule per minute. But where did it come from? It came from the physics. Specifically, came from Newton's work formula, the movement formula, where work equal force multiplied by displacement. By analogy, in respiratory system, pressures produce volume changes. Thus, stress replacing force and strain replacing displacement, and multiplying stress by strain allow us to achieve the work of breathing. The airway pressure reflects the stress applied to the lung and chest wall, and strain correspond to change in volume, in lung volume, that is the alveolar deformation. Therefore, work of breathing equal pressure multiplied by tidal volume. To conclude, if you enter with a period time, in this case 1 minute, you get the power of inspiration. And finally, if you put 0.98 as a conversion factor to transform it into joule per minute, we will get the mechanical power. But the inspiratory energy can be fragmented. Although the components of mechanical ventilation tend to be unified into mechanical power, perhaps the energy component needs to be fragmented. This Cartesian graph shows pressure on vertical line and time in horizontal line. Static power corresponds to potential energy stored in the respiratory system by the PEEP. Dynamic power corresponds to energy necessary to inflate the lungs. The sum of dynamic and static power result in elastic power. And the last fragment is kinetic power, which is the energy spent on overcoming and the airway and tissue resistance to the flow. The total inflation energy, that is the mechanical power, is equal to elastic power plus kinetic power. The fragmentation of the energy required to inflate the lungs may point to protective ventilation strategies effective to reduction of the risk of bleeding and may clarify the contribution of each component of the power to the generation of such injury. But how can it be measured? It can be accurately measured by the geometric methods or estimated by use equations. If you use the geometric method, measuring the dynamic inspiratory area of airway pressure and curve during the respiratory cycle, the calculation is performed using this point of greatest pressure and volume shown in the PV looping. In order to make it easier to use mechanical power, formulas were created for its calculation. There are several formulas as Gattinoni, Marini, Chiosa, Chai, Assar, Becker, van der Merwe, and each one has its own characteristics for obtaining mechanical power, such as need for an inspiratory pulse or not, average pulse pressure, work of breathing, etc. But still remain very long and very complex, these formulas, with the presence of integral, and that's why they created surrogate formulas. Remember that formulas are different for each ventilation mode. If you use Gattinoni surrogate formula, you need an inspiratory pulse to obtain plateau pressure, and from the result of subtracting the peak pressure minus driving pressure, and this result will be multiplied by tidal volume and respiratory rate and the factor to use when you calculate ventilation volume control. And if you use to pressure control ventilation, you can use Becker formula or van der Merwe. Becker just multiply peak pressure, volume tidal, and respiratory rate multiply 0.98. Absolutely, mechanical power should be included in the ventilator display. Mechanical power, because mechanical power is summary variable derived from solid physical and biological foundations that can be included in any ventilator to monitor safety of mechanical ventilation and guide lung protective strategies. In a sense, mechanical power is to ventilation what venous oxygen saturation is to body homeostasis, a variable that reflects the combination or different elements, arterial oxygenation, oxygen consumption, cardiac output, hemoglobin, all potentially associated with mortality. It's pointed out an elevated mechanical power, regardless of the combination of its components, can lead to V, especially when it exceeds 12 joule per minute, while over 17 joule per minute is associated with a higher mortality rate, and 19 to 24 joule per minute denotes the severity of hearts. Remember, protective ventilation is considered when tidal volume is maintained between 4 to 8 cc per kilogram of predicted weight, plateau pressure is less than 30 centimeters of water, driving pressure is less than 15 centimeters of water, and PEEP is maintained between 8 and 14 centimeters of water. However, doubts persist about the safer adjustments of mechanical ventilation components and parameters in ARDS to attenuated V. So, small adjustments make the ventilation protective. It seems that mechanical power can complement the adjustment of mechanical ventilation parameters. Even defined the plateau pressure, driving pressure, and tidal volume at values considered protective. Mechanical power in this case showed a limited value. Here's the question, can I improve? So the focus on energy reduction can help us with small readjustments of parameters with significant reduction, as long as ventilation and oxygenation are adequately maintained. In this case, the peak pressure was adjusted from 22 to 19 by reduction the inspiratory pressure from 15 to 13, and PEEP was reduced from 7 to 6 centimeters of water, in addition to respiratory rate from 20 to 18 per minute, and mechanical power reduced from 15.73 joules per minute to 10.44. Remember, mechanical power value between 7 and 212 joule per minute was associated with the lowest injury assessment during anatomical and physiological variables. As shown these slides, the values of mechanical power before and after small adjustments with a 30% reduction in transferred energy without damage to oxygenation and ventilation. By the way, over-ventilation must be avoided, and lower levels of mechanical power are always desired. But our show is just started, because this is not so logical. There is a tendency to replace the concepts based on tidal volume and pressures for understanding mechanical power as a Billy generator, but its predictive accuracy is still unclear. As we will see next, the results with different ventilation modes. In this research performed in severely burned patients undergoing pressure control ventilation, it showed that mechanical power in burned patients were elevated, and that regardless of mechanical ventilation time, these values are related to mortality, possibly because it portrayed the severity of the arts, as Maiolo found values between 19 and 24 joules per minute is associated to higher mortality. In this research, in the three groups, the average values of patients who died varied between 24 to 30 joules per minute. Although with a restricted number, it showed statistical significance. In next research performed in COVID with moderate arts undergoing pressure control ventilation, it showed that there is interference in the outcome in the univariate analysis of mechanical power and its components. But the multivariate analysis showed that only mechanical power correlate with the outcome in pressure control ventilation. In the next the research performed in COVID with moderate arts undergoing volume control ventilation, identify average values of mechanical power of 26.71 joules per minute. Despite the high values, the univariate analysis did not show difference in outcome, whereas the multivariate analysis suggests interference of mechanical power in the outcome, further estimating that every additional unit in mechanical power, there is an increase of 13.4% on the mortality risk. As well for higher elastance and lower PEEP values. This set of PEEP, elastance, and mechanical power multivariate analysis is very interesting in VCV. Note that indication of increasing mortality occurs with the reduction of PEEP values, increase elastance, and mechanical power. This refers to the lung that does not respond to recruitment and that needs a lot of propulsion force, keeping the mechanical power high. Hence, the more critical patients needed a greater propulsion force generated by the driving pressure to overcome the elastance of the pulmonary tissue, exhibiting low recruitability through the PEEP. Perhaps it's necessary to fragment the mechanical power to understand which portion of energy influence its highest values and what proportion, thus being able to suggest not only the severity but also the pulmonary prognosis. Although experimental studies revealed that isomechanical power achieve adjust tidal volume or respiratory rate, PEEP is responsible for the iso damage to the lungs, regardless the proportion of each of components. In our study, it was noticed that the proportion of fragments that compose the mechanical power had an influence on mortality, and that increased the dynamic power and decreased static power influenced the mortality rate of patients with COVID. Elevated mechanical power, regardless of the combination of components, can cause similar damage. However, the proportion of components to determine the same mechanical power can indicate the severity of arts with the possibility of really or reflect the temporal consequence of the conjunction arts and V. And captative ventilation. With smart adjustment can reduce mechanical power. Bench study using a lung simulator showed that adaptive ventilator delivered less mechanical power compared to two conventional modes using low tidal volume in a normal lung, and theoretically confer a mortality benefit in clinical practice, though this remains to be investigated. Important, using esophageal pressure as an estimate of the change in pleural pressure, it's possible to quantify the proportion of the total mechanical power which is delivered to the lung, an essential information for critical patients with different chest wall elastance. But in fact, in this way, mechanical power may not represent alveolar pressure and tidal pressure. So, going deeper, the concept of alveolar compliance depends on measurement of transalveolar pressure using esophageal balloon manometry and alveolar tidal volume using volumetric capnometry. The knowledge of alveolar dynamics and mechanics in critically ill are lacking, with much information originating mainly from bench and animal modes of health and injured lungs. In this article, we introduce the concept of alveolar compliance resistance that depend on measuring the transalveolar pressure using esophageal balloon manometry and alveolar tidal volume using volumetric capnometry. There is a tendency to replace the concepts based on tidal volume and pressure for understanding mechanical power as a Will generator, but its predictive accuracy is still unclear. Arts and Will merge into a virtually unique and complicated form of lung injury where the relative contributions are indistinguishable and are attributable as the cause of death individually. Which way to go? Determine a protective value for mechanical power based on lung size, age, and sex. Search for the best combination of ventilatory components that achieves that lowest mechanical power compatible with adequate gas exchange and hemodynamics. And the expectative uh, if you wait. Mechanical power is very recent and its research is mostly experimental or based on its correlations with results. Therefore, we still do not know for sure the amount and time needed for the energy delivered by the ventilation to the pulmonary system to cause injuries. And that these also depend on lung condition and utilities. What is the lowest mechanical power for a given pulmonary situation that can maintain adequate ventilation and oxygenation variable? In this moment, keeping the focus on energy reduction can help us with small readjustment of parameters with significant reduction as long as ventilation and oxygenation are adequately maintained. In the next future, real-time monitoring of mechanical power coupled in two ventilators and the amount accumulated during ventilation time with the best combination of components that achieves the lowest mechanical power based lung size, age, and sex. And if you wait anymore, who knows? Intelligent ventilation controlled by alveolar mechanical power. Personal opinion. Uh, ventilation circulation integrated by continuous monitoring of ventilatory mechanics, macro and microcirculatory hemodynamics, and partial pressure and gas exchange, with it automatically adjusted to achieve the stipulated mechanical power, that is, energy control ventilation. A ventilator that enables energy control ventilation may appear in which the software will control mechanical ventilation by the established value of mechanical power, but will maintain a search for its value considered normal, with continuous adjustment to find the best set of flow, respiratory rate, tidal volume, driving pressure, and ideal PEEP, considering the resistance, compliance, and elastance of the lung moment to maintain the partial pressure of oxygen and carbon dioxide within established limits with the lowest fraction of inspired oxygen. Thank you very much.